Right, guys, so now I'm just going to go through how you'd perform a one-way between factor ANOVA in SPSS. So this is slightly different to the one-way repeated factor ANOVA, which I'll go through in a separate video. So this is a one-way comparing between groups rather than, for example, over time. So typically when you would use a one-way ANOVA when you're comparing more than two means. So comparing two means, typically you'd run a paired t-test or an independent t-test depending on your experimental setup. So this has one independent variable. So this could have 3 groups, 10 groups, it wouldn't matter as long as you just have one independent variable. But the between factor ANOVA is where the groups are independent from one another. So if it was a repeated ANOVA, then those groups would be related. So you might be comparing over time, over multiple days. Here, we'd use a between factor ANOVA if you're comparing between different conditions, between different cell types, etc. But the repeated ANOVA and the between ANOVA are similar in that you have one independent variable and where you have more than 2 groups or 2 conditions that you're comparing against one another. And for this between factor ANOVA, it typically has 2 main assumptions. So the data has to be parametric. This is a parametric test, so it has to follow a normal distribution. If not, you can run the non-parametric equivalent, which is this Kruskal-Wallis or KW test. And then secondly, that the variance or the standard deviation is equal across groups within that independent variable. So if you've got 3 groups or 10 groups, that the error is not too different across those groups. If it is, then you can use an alternative. So you can check this with Levine's test, but the alternative would be something like a Welch ANOVA or even a Brown-Forsyth ANOVA. So you can have a situation where you have normal distribution, so the data is parametric, but you have unequal variance. So in that case, you might run a Welch ANOVA, or you might have a situation where you have equal variance, but your data is not parametric, so you could run a Kruskal-Wallis test. You might end up where both of the assumptions are met, where you just run the normal ANOVA. You might have a situation where both of these assumptions are violated, so you have to make a decision based on what you find during these initial measurements. And then your ANOVA will tell you that there might be a difference, but it doesn't tell you where those differences are. So that's what your post-hoc tests are typically used for. So where do those differences lie? So if you've got 3 groups, is it group 1 versus group 2, group 1 versus group 3, or group 2 versus group 3, where those differences lie? You can find that out using these post-hoc tests. So I'm just going to give a very simple example. So for this particular between factor ANOVA, we can have 3 groups. Again, you could have 10 groups, you could have 100 groups. As long as it's one independent variable, then it will just be a one-way ANOVA. And this is just an extension of the data in previous videos where I've done t-tests. Here I've just added an extra group. So instead of running multiple t-tests, we'll just run a one-way ANOVA, so we can keep that error rate at 5%. So here we've got 3 biological replicates, we've got 3 groups. And then here, this is just some made-up data indicating resting heart rate. So if you look at the figure, it seems that heart rate goes up. So it's the highest in group 3 relative to group 1, and group 2 is higher than group 1. So it looks like there's a difference, but we'd have to run the ANOVA to find out if there is a difference across these groups, and then post-hoc test to determine where those differences lie. So this is different groups, but measured at the same time. If it was the same group, so group 1, day 1, group 1, day 2, group 1, day 3, then we might run a repeated factor ANOVA because those groups would be related or dependent on one another. Okay, so, but first we want to check for normality and equal variance. So the typical pipeline, if you like, that I'd use is I'd check the normal distribution and then the equal variance. Then depending on what we find there, we choose the most appropriate ANOVA to run. So a normal one-way ANOVA, if both of these assumptions are met, or a Kruskal-Wallis test, if the data is not parametric, or a Welch ANOVA, if the data does not have equal variance. And then there are specific post-hoc tests you'd use depending on what ANOVA you run as well. So do you run a Bonferroni, a Tukey, a Dunnett? That's if you have parametric data, that assumption's been met. If you run a Kruskal-Wallis test, typically you'd run a Dunn post-hoc that has a Bonferroni correction, or you'd run a Games-Howell post-hoc if you had unequal variance. So if you run a Welch ANOVA, typically you'd run the Games-Howell post-hoc for that. All right. So we can go now and look at some of our data. So here we just essentially copy and paste this into SPSS, but I haven't set up the spreadsheet yet, so we can do that. So if we want to create our variable for a between factor ANOVA, we need to create a nominal variable. So we can call this, let's say, group. Okay. You have to list it as a nominal variable, otherwise SPSS automatically converts it to scale, which we don't want. And then we're going to have 3 groups. And then 2 we'll call group 2. And then 3 we'll call group 3. Okay. And then we need a scale variable to denote heart rate. I'll just list it as scale. You don't need to because it will automatically do that. Okay, so we've got 3 replicates in each group, so we can go 1, 1, 1, 2, 2, 2, 3, 3, 3. And then you can just click this here to check, convert it to your code that you gave your group. I keep it on this one just so I can see which group it is. And you can basically just copy and paste that. So if I have group 1, and then group 2, and then group 3. Okay. So first I'm going to check for normality, because you can run that independent of the actual ANOVA. When you run the equal variance, you typically run that at the same time as the ANOVA. So here we go, descriptive, statistics, explore. So group is our nominal variable or our factor. And then heart rate is our dependent variable, so I can go in the dependent list box. And then I go into plots. I just turn off these. I just want my normality plots with tests, but you feel free to play around here. Okay, so we get output, a lot we don't need, but this is the one we want, test of normality. So we want Shapiro-Wilk because that's for smaller sample sizes. The Smirnov test is for larger sample sizes. We've not got an output. So here we're looking for higher than 0.05. So all of these are higher than 0.05, group 1, group 2, group 3. So that assumption has been met. If you had 10 groups, you'd have 10 p-values. So I have 3 levels within this factor because I have 3 groups. If I had 10 groups, I'd have 10 levels, and you'd have 10 p-values. The Levene's test for equal variance is different. You just get 1 p-value for your entire independent variable. But here this is fine, so okay, the data does seem to be normally distributed. So now we can actually run the ANOVA and ask for the equal variance check at the same time. So here to run the ANOVA, here we go, analyze. We can run it a couple of ways, but I'm just going to run it the way I do, compare means, and then one-way ANOVA. If we had a repeated factor ANOVA, we'd have to go to general linear model, repeated measures. But here we're just going to go compare means, one-way ANOVA, which is just another way of saying one way between factor ANOVA. So here group is our factor, heart rate is our dependent variable. Okay, post-hoc test. So let's just click a few here. So we can have SIDAC as well, Bonferroni. Bonferroni is quite conservative. I normally go for 2 key, or if I'm just comparing against a control, I can just choose Dunitz, and you can determine which is your control group. So we'll look at the output for all these. And then equal variance not assumed. So this is if the Levene's test has been violated. We can click Games Howl. So I'm going to click that as well. So we're going to get quite a lot of output. Options, this is where we have to choose Levene's test. They don't call it Levene's test, they call it homogeneity or variance test. So we can click that. We do actually need this. Descriptive, that's nice. And then if this is violated, we can run the Welch ANOVA. So if we tick that, it will run the Welch ANOVA at the same time. So we're going to get quite a lot of output here, but that's fine. We can just tick it all off in one go. Okay, so here we've got group 1, group 2, group 3, gives us our mean, our standard deviation, our standard error, the number of biological replicates within each of these groups, which we know is 3. So for Levene's test, it's given it as in this output. Typically we want the top row, so heart rate based on mean. is 0.151, so that means it's higher than 5% or 0.05, which means the assumption has been met. So the variance across our groups is equal. So we have parametric data, we have equal variance, so we can accept to run a normal one-way ANOVA. We don't run a Kruskal-Wallis test, we don't run a Welch ANOVA, anything like that. And this is the output that we want from that specific ANOVA, and it's telling us that it is significant. So there is a difference across our groups, we just don't know where that is. We've also got the Welch ANOVA here. We don't need this p-value, so if we were going to report the p-value in the paper, we'd use this one, not this one. If we had unequal variance, we could use this one, but it doesn't matter, they're both significant. It's telling us the same story. So our post-hoc tests, this is where we compare the different groups against each other. So the one thing Bonferroni and Tukey and even Games Howell will do is they compare everything against each other. So we take Tukey, it's compared group 1 versus group 2 and given us the p-value. Then it's compared group 1 versus group 3 and given us the p-value. Then it's done all the different combinations, right? So I can just look down here and say they're all different. So all of the groups are different from each other. Bonferroni does the same thing. Bonferroni is a bit more conservative. You'll see slightly higher p-values, but even here they're all significantly different. This is on the border, 0.047, whereas with Tukey is 0.036, but they're still significant. Games Howell is more conservative than Bonferroni, so the most conservative out of these. You can see this one's not significant now, 0.082, but we don't use this anyway because this is when we have unequal variance. And then Dunnett is different. It just compares everything to the control. So I said group 1 is my control, so it's just gone group 2 versus group 1, group 3 versus group 1, but it doesn't compare group 2 versus group 3 because neither group 2 nor group 3 are the control. Right, group 1 is the control that I've told it. Right, so that's the only other thing I've got to do is if you want to run a Kruskal-Wallis test, let's just assume that the data is not normally distributed. Let's assume here, for example, that all these or 2 of these or whatever were less than 0.05. We can go to analyze, we can go to non-parametric test, we can go to independent samples. If we had a repeated ANOVA, we might go to related samples, but let's just go to independent samples. And then we can go to field. Group is our group, heart rate is our dependent variable. We can go to settings, customize tests, and we can go to Kruskal-Wallis, one-way ANOVA. And we can say all pairwise, okay, fine. So this is going to run the non-parametric test. And even here it's saying that it's significant, 0.027, slightly higher p-value. The other one was less than 0.001, but now it's saying the distribution of heart rate is the same across categories or the group, and it's basically saying reject the null hypothesis. It's saying no, heart rate is different across the groups. And then you get a nice figure as well showing that group 1 versus group 2 versus group 3 are different. But the pairwise comparisons are not significantly different this time apart from group 1 versus group 3. So if we compare this one, which is the lowest, versus this one, which is the highest, they're different, but group 2 isn't different from either. We wouldn't use this anyway because we have normal distribution. We have parametric data, so we wouldn't ever run this test on this type of data, but it's just so you can see how to do it. All right, I'll leave it there. Thanks very much for listening. Please like the video and subscribe for more content. All right, I'll see you on the next one.